Welcome back to the Deep Dive, your shortcut to cutting through the noise and truly understanding what makes our digital world tick. Today, we're diving deep into the intricate foundations of digital system design. We're talking about the core logic that powers pretty much everything around us. We've really dug into a comprehensive research plan on this for you. And our mission today is, well, to distill those complex concepts into clear, actionable insights. Think of it as a crash course in the silent language of zeros and ones.
Exactly. We've got 5 crucial areas to unpack. We'll start with the brains of these systems, finite state machines. Then we'll explore the tricky art of communicating between different parts of a chip, which is clock domain crossing. We'll also uncover those hidden gotchas in signal timing, known as hazards. Then shift to the fundamental math that makes computing possible, arithmetic circuits. And finally, touch on a key design choice within FSM's Mealy versus Moore.
And trust me, by the end of this deep dive, you'll have a new appreciation for the surprising connections and, frankly, the clever trade-offs that engineers constantly wrestle with. This is your chance to truly be well-informed about the invisible logic beneath your fingers. Okay, let's unpack this. So let's start with the absolute core. What exactly are finite state machines, or FSMs? I mean, think about a simple light switch, right? It's either on or off. That's it. Its output just depends on what you do right now. FSMs are different. They're the control backbone of digital systems because, well, unlike that simple switch, they have a memory element. This means their current output isn't just about the immediate input, but also what happened moments ago. It's its ability to kind of remember prior conditions that's fundamental for any complex sequence.
That's spot on. Think of an FSM as a system that can be in one of several states at any given time, each state representing a unique configuration or memory of past events. It moves between these states, we call these transitions, when certain inputs are received, often synchronized to a common clock signal. And as it transitions or sits in a state, it produces specific outputs. We almost always design synchronous FSMs because tying all state changes to that common clock makes their behavior predictable, reliable, and frankly, much easier to debug.
Predictability, right?
Yeah. Dealing with inputs that aren't synchronized or signals coming from different clocks, that introduces entirely new layers of complexity we'll get into later.
And how do engineers actually visualize and build these? I mean, conceptually.
Well, they often start with state diagrams, which are basically flowcharts, nodes for states, arrows for transitions, showing the conditions and outputs.
Okay.
Or they use state tables, which are just, tabular versions, current state, inputs, next state, outputs.
And physically, what are they made of?
Physically, they're built using tiny memory cells called flip-flops, usually D flip-flops, to hold the state information. And then standard combinational logic, gates ANDs, ORs, NOTs, that figure out the next state and the outputs based on the current state and inputs.
Got it. So you've probably interacted with FSMs without knowing it then.
Absolutely. They control everything from a simple traffic light sequence.
Makes sense. Red, yellow, green.
Exactly. Or a vending machine, you put money in, press a button, it remembers what you did, dispenses the item, or even like a basic 2-bit counter.
Right. And designing one isn't just random, is it?
Oh, no. It's a very structured process. First, you have to really understand and define what the FSM needs to do. Inputs, outputs, required behavior. Then you map out your state diagram visually.
It's a chart thing.
Right. From that, you derive the state table. Then comes a really critical decision, state assignment, or encoding.
Encoding. What's that?
That's where you decide how to represent each unique state using binary codes, zeros and ones for your flip-flops. And this choice, it's a core engineering puzzle because how you encode the states directly impacts the circuit's performance, its size, its speed, even power consumption.
Ah, okay. So there are different ways to do it.
Yes, several key strategies. You could use binary encoding that uses the absolute minimum number of flip-flops needed, log base 2 of the number of states.
Efficient on space, then.
Very efficient on area, yes. But it often makes the logic needed to calculate the next state much more complex, potentially slower.
I see. So what's the alternative?
A popular one is one-hot encoding. Here, each state gets its own dedicated flip-flop. So if you have 8 states, you use 8 flip-flops.
That sounds like it uses more space.
It definitely uses more silicon area, significantly more sometimes. But the upside is it vastly simplifies the next state logic, which often makes the FSM much faster. There's also gray code encoding, where adjacent states differ by only 1 bit, which helps reduce glitches and power.
So it's a trade-off. Area versus speed, maybe power too.
Exactly. It's a classic example of a fundamental design trade-off. You're balancing area versus speed versus power versus even testability. Achieving an optimal FSM design is rarely about just maximizing one metric. It's a multi-objective optimization problem. What's most important for this specific application?
Okay, so once you've chosen the encoding.
Then designers use techniques like Carnot maps or software tools to minimize and simplify the logic equations for the next state and outputs. And finally, they implement the circuit, usually by describing it in a hardware description language or HDL like Verilog or VHDL.
That's right, for abstraction.
Yeah, essential for managing the complexity of real-world designs.
Now, here's where it gets really interesting, because FSMs, despite being powerful, they face some serious real-world challenges, right?
Oh, absolutely. One of the biggest is state explosion. As you add features, the number of possible states can grow exponentially. This makes complex designs incredibly difficult to manage, verify, or even simulate completely. Scalability becomes a huge issue.
So, too many states to handle. What else?
Well, you can run into deadlocks, where the FSM gets stuck in a certain state or loop and can't progress, very bad, or race conditions, where the final state becomes unpredictable because the timing of signals arriving at the logic gates is just slightly off.
Timing. Always tricky.
Always. And then there are more subtle physical issues. Things like metastability, where a flip-flop doesn't settle cleanly to a 0 or a 1, but gets stuck in some unstable intermediate voltage level.
Uh-oh.
Yeah, and glitches, which are these unwanted transient spikes or dips in signals that can cause chaos if they happen at the wrong moment.
So any of these can lead to a system that just doesn't work right or works unpredictably. And I imagine they're hard to find.
Incredibly difficult to find and debug, especially the timing-related ones and metastability.
So how do designers fight back against these problems?
They rely on powerful analytical techniques. Simulation is the workhorse. You run virtual tests, apply inputs, observe outputs, try to catch bugs. But simulation has limits. It can only show you bugs that are present in the scenarios you test. It can't prove that bugs are absent.
Right. You might just miss the one case that breaks it.
Exactly. That's where formal verification comes in. This is a huge advancement. It uses mathematical proofs to analyze the design. It can actually guarantee correctness for certain properties, like proving the absence of deadlocks across all possible states and inputs. It's much more rigorous than simulation.
Mathematical proof. Wow. Okay. What else?
And then there's static timing analysis, or STA. This specifically focuses on the timing. It mathematically checks all the signal propagation delays through the logic paths to ensure signals arrive exactly when they should, meeting those critical setup and hold times we'll talk more about later.
Okay, so we have simulation, formal verification, STA. What about design techniques to make FSMs more robust from the start?
Good question. Engineers use techniques like state minimization to reduce the number of states logically without changing the behavior. That helps with the state explosion. And as we discussed, carefully choosing the state encoding scheme is critical for optimizing speed, area, and power. Building safe state machines is another key concept designing them. So if an unexpected error does occur, the machine transitions to a known, benign, maybe a reset state, rather than locking up.
Damage control.
Pretty much. And robust reset logic is absolutely non-negotiable for bringing the FSM to a known starting point. For pure performance, techniques like pipelining and retiming are critical for breaking down logic paths and pushing clock frequencies higher.
So where do we see these FSMs in the real world? You mentioned traffic lights.
Oh, they are ubiquitous. Absolutely everywhere. Traffic light controllers, yes. Vending machines, definitely. Managing communication protocols, things like UART, SPI, I2C, that let different chips in your phone or computer talk to each other. Those rely heavily on FSMs to manage the sequence of signals. And perhaps most critically, the central control unit within any central processing unit, the CPU. That's fundamentally a very complex FSM. It dictates the fetch, decode, execute cycle.
The brain's brain, almost.
In a way, yes. So understanding FSM design is really a core competency, a foundational skill for any digital designer. Their principles underpin virtually every sequential digital system out there.
Okay, so FSMs give our systems their intelligence and control. That makes sense. But what happens when different parts of that system need to communicate, especially if they're thinking at different speeds, running on different clocks?
Ah, yes. That's where clock domain crossing, or CDC, comes in. This is all about transferring signals between parts of a digital system that are running on different asynchronous clocks.
Why would you even want different clocks in the same chip? Doesn't that just complicate things?
It does complicate things, but it's often necessary. A big reason is power optimization. You don't need every single part of a chip running at maximum speed all the time. You can slow down less critical parts to save power.
Okay, power saving. Makes sense.
Also, for performance optimization, you might want a critical processing core to run much faster than, say, a peripheral interface. And very commonly today, for integration of IP cores, these are pre-designed blocks, maybe from third parties, that often come with their own specific clock requirements.
Like building with advanced Lego bricks that have their own batteries.
Kind of, yeah. And sometimes you need to interface with older legacy systems that operate at different clock speeds. So CDC isn't really a design flaw to be avoided. It's more an inherent challenge of modern, complex system design that we have to manage very, very carefully.
And what's the biggest headache with CDC?
The absolute most critical, most notorious issue is metastability. We touched on it briefly with FSMs. It happens when a signal being received by a flip-flop changes its value too close to the active edge of the receiving clock. The flip-flop can then enter an unstable, indeterminate state for an unpredictable amount of time. It's neither a clear 0 nor a clear 1.
So the signal is just uncertain.
Exactly. And here's the crucial part. It's not a deterministic error you can just design out completely. It's a probabilistic failure mechanism.
Probabilistic. Like it might happen, might not.
Precisely. Think of it like a tiny, unfixable flicker or glitch whose probability depends on timing relationships and device physics. Designers can only reduce the probability of a metastable event causing an actual system failure down to an acceptably low level, usually an incredibly low level.
Wow.
This forces a shift in thinking towards statistical reliability and designing for a target mean time between failures, or MTBF. You aim for an MTBF of, say, thousands of years for critical systems.
So you can't guarantee it never happens, just that it's astronomically unlikely to cause a problem within the device's lifetime. That's a bit unsettling.
It is, but it's the physical reality we work with.
Okay, so if you can't eliminate it, what's in the toolbox to handle this probabilistic headache? How do you reduce that probability?
The most common technique, almost the default for single-bit control signals, is the 2 flip-flop synchronizer, often called a 2FF synchronizer.
2 flip-flops in a row.
Yes, you pass the incoming asynchronous signal through 2 flip-flops clocked by the receiving domain's clock. The first flip-flop might go metastable, but by the time the signal reaches the second flip-flop 1 clock cycle later, the probability that it's still metastable is drastically reduced.
So it gives it time to settle down.
Essentially, yes. It adds latency, usually 2 clock cycles of the receiving clock, but it significantly increases the MTBF against metastability-induced failures.
Okay, that's for single bits. What about transferring like a whole chunk of data?
For multi-bit data streams, especially bus-based data, the 2FF approach alone isn't usually sufficient because different bits might arrive at slightly different times. For that, we often use an asynchronous FIFO, or first-in, first-out buffer. It's a small memory that sits between the 2 clock domains.
A buffer, okay.
It uses clever techniques, often involving gray-coded pointers, to manage the read and write operations independently in each clock domain without causing synchronization issues.
Gray codes again. Keeps popping up.
They're very useful because only 1 bit changes between adjacent counts, which helps avoid issues when reading the pointer value across a clock domain.
And any other techniques.
For control signals that need to ensure data validity, simple handshake protocols are often used. One side sends a request signal, the other sends an acknowledge signal back once it's ready or has received the data. It's a more robust but slower way to ensure a safe transfer.
Request acknowledge, like a formal agreement.
Exactly. More overhead, but safer for critical control.
So what are the key rules designers have to follow when dealing with CDC?
Discipline is absolutely critical. First, you must clearly identify and properly constrain every single signal path that crosses a clock domain boundary in your design. Tools can help, but designer intent is key. Second, always use dedicated, proven synchronizer circuits, like the 2FF or FIFOs for these paths. Don't try to get clever with custom logic here. Third, a major no-no. Avoid placing any combinational logic directly in the path right before a synchronizer flip-flop in the receiving domain. That logic can introduce glitches which completely undermine the synchronizer.
Okay, keep it clean right before the synchronizer.
Yes. And finally, even fundamental signals like reset need careful synchronization if they need to deassert across different clock domains simultaneously. Reset synchronization is often overlooked but crucial.
Got it. So we've talked about FSMs for control and CDC for communication between different clock speeds. But even within the same clock domain, signals aren't perfect, are they? Let's talk about hazards and timing issues in just regular combinational logic.
Right. Even without clock domain boundaries, the physical reality of signals taking time to travel through wires and gates causes problems. Hazards are essentially unwanted, temporary glitches or spikes that can appear at the output of a combinational circuit.
Glitches again.
Yes, but these happen within a single clock domain, usually due to different propagation delays along different paths leading to the same output gate.
So one signal path is faster than another, and they don't arrive quite simultaneously.
Exactly. Imagine two signals feeding into an AND gate. If one goes low slightly before the other goes high, the output might momentarily dip low when it should have stayed high. These are momentary, incorrect outputs that reveal the non-ideal, time-based nature of physical circuits.
Are there different kinds of these hazards?
Yes, we categorize them. Static hazards occur when an output signal is supposed to remain constant, either 1 or 0 low, during an input change, but it momentarily glitches to the opposite value before settling back. We call them static 1 hazards, should stay 1, dips to 0, or static 0 hazards, should stay 0, spikes to 1.
Okay, so static means it should have stayed still but didn't.
Correct. Then there are dynamic hazards. These happen when the output is supposed to change state, say from 0 to 1, but it changes multiple times, like 0 minus 1 minus 0 minus 1, before finally settling at the correct value. More like a bounce.
That sounds messy.
It can be. And there are also function hazards, which are a bit different. They're inherent to the logic function itself when multiple inputs change simultaneously. You sometimes can't eliminate these just by adding gates.
So what's the real danger of these glitches? They're just temporary, right?
They are temporary, but the critical impact comes if one of these momentary glitches happens right around the time a clock edge arrives at a flip-flop that's supposed to capture the output of that combinational logic.
The timing again.
Exactly. If that glitch gets latched or captured by the sequential element, the flip-flop might store the wrong value. This can lead to completely unpredictable and incredibly difficult to debug system behavior down the line. A seemingly innocent combinational glitch can have profound sequential consequences.
Okay, so glitches are bad if caught by flip-flops. What about other timing issues in sequential circuits?
Beyond hazards, there are fundamental timing rules that must be met for reliable operation. The most critical are setup time and hold time.
Set up and hold. Heard those terms.
Setup time is the minimum amount of time the input data signal must be stable before the active clock edge arrives at the flip-flop. The flip-flop needs time to see the data before it tries to capture it.
Okay, data needs to be ready early.
Right. And hold time is the minimum amount of time the input data signal must remain stable after that same clock edge has passed. The flip-flop needs the data to stay put for a moment while it grabs it.
Don't change it too soon after the clock.
Exactly. Violating either setup or hold time can lead to metastability or capturing the wrong data. Then there's clock-to-Q delay, which is simply the time it takes for the flip-flop's output Q to actually change after the clock edge arrives. It's the propagation delay of the flip-flop itself.
So how long it takes to react?
Yes. And these parameters set up time, hold time, clock-to-Q delay, plus the delays through the combinational logic between flip-flops fundamentally dictate the maximum clock frequency your circuit can reliably operate at.
They set the speed limit.
They absolutely set the speed limit. We also have to worry about clock distribution itself. Clock skew is the difference in arrival times of the same clock edge at different flip-flops on the chip.
So the clock doesn't arrive everywhere at the exact same instant.
Not perfectly, no. There are always slight delays. Minimizing skew is critical. And clock jitter is the cycle-to-cycle variation in the clock period itself. The clock isn't perfectly regular.
Wow, lots to worry about with timing. How do designers deal with hazards and meet these timing constraints?
For hazards in combinational logic, a common technique involves using Karnaugh maps during design to identify potential hazards and then strategically adding redundant logic gates.
Adding extra gates. Doesn't that increase size?
It does, slightly. But these redundant gates effectively hold the output stable during transitions where a glitch might otherwise occur. It's like adding a temporary backup path.
Okay. And for the setup hold time issues and speed limits?
That involves a range of strategies. Optimizing logic paths to reduce the delay through combinational logic is key. Simplifying logic, using faster gates. We mentioned pipelining earlier for FSMs. It's crucial here too. You break long combinational paths by inserting flip-flops. pipeline stages. This increases latency for a single operation but boosts overall throughput by allowing a higher clock frequency.
Trading latency for throughput.
Often, yes. Retiming is a more advanced optimization where tools move existing flip-flops around, shifting logic across register boundaries to better balance delays between stages without changing the functionality. And for clock skew and jitter, enormous effort goes into clock tree synthesis, CTS, during physical design. This builds a dedicated network to distribute the clock signal as evenly and precisely as possible across the entire chip.
So how do they know if they've met all these timing rules across a huge, complex chip? Simulation seems impossible for checking everything.
You're absolutely right. Simulation can't cover all paths and all conditions. The absolute cornerstone of modern timing verification is static timing analysis, or STA.
STA again, so this is really important.
Hugely important. STA doesn't simulate the circuit's function. Instead, it performs a mathematical analysis of all possible signal paths between clocked elements in the design. It uses timing models for gates and wires to calculate the signal propagation delays along every path and checks if setup and hold times are met, usually under worst-case conditions. Slow process, low voltage, high temperature.
So it provides a guarantee.
It provides a mathematical guarantee of timing correctness, assuming the models are accurate. It finds the critical path, the slowest path that limits the clock speed. It's a fundamental shift from just finding timing bugs with simulation to proving timing correctness.
So what does this all mean? Why is mastering CDC and timing so critical?
Because this expertise managing CDC safely, eliminating hazards, meeting stringent timing constraints using STA, is what allows engineers to truly push the boundaries of chip performance and power efficiency. It's indispensable for designing the complex systems-on-chip, SoCs, in your phone, powerful multi-core processors, high-speed memory interfaces like DDR, and basically any high-speed processor or communication chip made today. It enables modularity, performance, and efficiency all at once.
Okay, that makes a lot of sense. Control, communication, timing.
Quote.
What about the actual number crunching? Let's talk about the true workhorses.
Yeah.
Arithmetic circuits.
Yes, the computational engines, these are absolutely foundational building blocks. They handle the core math operations, addition, subtraction, multiplication, division. You find them everywhere, from the main CPU in your laptop to the specialized graphics processing units, GPUs, in gaming consoles or AI accelerators. They're doing the heavy lifting of computation.
When designers build these, what are they aiming for? Just speed.
Speed or low latency is usually very important, yes. How quickly can it perform one calculation? But it's rarely the only factor. Designers are always balancing several critical metrics. Speed, area, how much silicon real estate it takes up, power consumption, crucial for battery life and heat, and sometimes throughput, how many calculations it can start or finish per second, which isn't always the same as latency.
So another set of trade-offs.
Absolutely. This defines a fundamental design trade-off space for arithmetic circuits. Optimizing heavily for one metric almost always means compromising on another. For instance, a super fast multiplier might be enormous and power-hungry. A tiny adder might be quite slow. So designers rarely achieve perfect arithmetic circuits in every respect. Instead, they aim for optimal circuits, carefully tailored to the specific constraints and requirements of the application. Finding the right balance for the job is key.
Right. So let's start with the most basic operation addition. What are the building blocks there?
It starts with half adders, which can add 2 single bits, producing a sum and a carryout bit. Then you have full adders, which add 3 single bits, 2 input bits, plus a carry-in bit from the previous stage. This is the fundamental block for multi-bit adders.
Okay, half and full adders. How do you build bigger adders from those?
There are many different architectures, again with trade-offs. The simplest conceptually is the ripple carry adder, or RCA. You just chain full adders together, one for each bit position. The carry out of one stage becomes the carry in for the next.
Like a chain reaction.
Exactly. It's compact, uses low area, easy to understand, but it's inherently slow, especially for wide adders, like 64-bit, because that carry signal has to literally ripple sequentially from the least significant bit all the way to the most significant bit.
So the last bit has to wait for all the previous ones.
Precisely. Each stage depends on the previous one. That severely limits the speed.
How do you get around that? Make addition faster.
To overcome this speed limitation, designers use more sophisticated architectures. A classic example is the carry look-ahead adder, or CLA. The key innovation here is that it uses extra logic to pre-calculate the carry signals in parallel for groups of bits, or even for all bits simultaneously in some variations.
Look ahead. So it figures out the carries faster.
Yes, it anticipates the carries without waiting for them to ripple through. This dramatically reduces the addition delay, allowing for much faster operation.
But there's a catch, right?
Of course, the catch is more complex logic and a larger area footprint. The look-ahead logic itself takes up space and consumes power. But this perfectly exemplifies that core design principle. You often move from purely serial computation, like RCA, to more parallel computation, like CLA, to achieve higher speed, at the cost of complexity and area.
Are there other adder types too?
Yes, there are intermediate designs like carry-select adders and carry-skip adders that offer different points in the speed-area trade-off space, trying to get some speed up over RCA without the full complexity of CLA.
Okay, that covers adders. What about multipliers? They seem much more complex.
Well, they're significantly more complex, fundamentally involving repeated additions and shifting. A basic approach is the array multiplier, which directly implements the grade school shift and add algorithm using an array of adders. It's regular but can be slow and large for wide inputs.
Any smarter ways to multiply?
Definitely. For more efficiency, especially with signed numbers, Booth's algorithm is widely used. It cleverly recodes one of the operands to reduce the number of partial products that need to be generated and summed. Fewer additions mean faster multiplication.
Fewer steps, faster result.
Right. And for very high-speed multiplication needed in things like DSPs and graphics, designers often turn to tree-based structures like the Wallace tree multiplier. This uses a tree of specialized components called carry-save adders, CSAs, to very quickly reduce the many partial products down to just two numbers. Then a final, fast adder, like a CLA, sums those two numbers.
A tree structure. Sounds fast, but may be complicated to lay out.
Exactly. Wallace trees are typically very fast, but have an irregular structure, which can make the physical design and layout on the chip more challenging compared to a regular array multiplier. Another trade-off.
And how do these adders and multipliers fit into the bigger picture, like in a CPU?
They are often combined, along with logic operations, AND or XOR, etc., and shifting capabilities, into a single versatile unit called an ALU, or arithmetic logic unit.
The ALU. Heard of that one too.
Yeah, the ALU is really the computational heart of most processors. It can perform a wide range of operations, selected by control signals, and guess what often generates those control signals?
Let me guess. An FSM.
You got it. A finite state machine in the processor's control unit tells the ALU whether to add, subtract, multiply, AND, or etc. based on the instruction being executed.
It all connects back. Now, you mentioned wider inputs, like 64-bit numbers. Does complexity just scale linearly? Double the bits, double the size?
Unfortunately, no. That's a key challenge. For many arithmetic circuits, especially multipliers, the complexity in terms of area and sometimes delay scales non-linearly with increasing bit width. It might scale quadratically, like n squared, or sometimes even worse. So simply increasing bit width is not a trivial scaling operation. A 64-bit multiplier is significantly more than twice as complex as a 32-bit one.
So going from 32-bit to 64-bit computing was a major leap in circuit complexity, not just data path width.
A very major leap. It forces designers to constantly look for more efficient architectures and algorithmic optimizations as bit widths continue to grow for applications like scientific computing or cryptography.
So faced with this nonlinear scaling and the usual trade-offs, what are the key solutions designers rely on for efficient arithmetic circuits?
Well, first and foremost, it's the judicious choice of architecture. Picking the right type of adder or multiplier for the specific performance, area, and power budget of the application. No single architecture is best for everything. Pipelining is absolutely crucial for high-throughput arithmetic. Just like with general logic, you insert registers, flip-flops, within the arithmetic circuit to break long calculation paths into shorter stages.
So each stage is faster, allowing a higher clock rate.
Exactly. It increases the number of cycles to get one result, latency, but you can start a new calculation every cycle, dramatically increasing the overall throughput, essential for things like signal processing. We mentioned carry-save adders, CSAs, used in Wallace trees. They're a key technique in multipliers to speed up the summation of many partial products by deferring the full carry propagation until the very end. And algorithms like Booth's algorithm provide efficiency gains, particularly for signed multiplication, by reducing the workload upfront.
So where do these optimized arithmetic circuits have the biggest impact?
They are the undisputed computational backbone of nearly all digital systems. Their efficiency and performance directly impact CPUs, integer and floating point units, GPUs, which are massively parallel arithmetic engines, especially for floating point needed in graphics and AI, and digital signal processors, DSPs. DSPs are specifically designed for applications like audio and video processing and often feature specialized ML units. Multiply accumulate units, which are highly optimized pipeline multipliers and adders. You also see specialized arithmetic heavily used in image processing hardware and cryptographic hardware for things like encryption and decryption, which involve intensive computations on large numbers.
And the trend is towards more specialized units.
Very much so. The trend is increasingly towards domain-specific acceleration. Instead of relying solely on general-purpose CPUs, systems incorporate specialized hardware units optimized for specific tasks, like AI accelerators or video encoders-decoders. This leads to a heterogeneous mix of processing elements, general-purpose cores, alongside various specialized arithmetic accelerators, all working together, each optimized for its specific computational niche.
Wow, what a journey through the fundamental building blocks of our digital world. It really puts things in perspective. We started by seeing how finite state machines provide that crucial control and memory, allowing systems to, remember past inputs and react intelligently.
Right, the decision-making core.
Then we dove into the complexities of clock domain crossing, how chips manage signals between parts running at different speeds, and grappling with that tricky probabilistic hurdle of modest stability.
A necessary evil in complex designs.
And then we explored hazards and timing issues, those real-world challenges of signal propagation delays and glitches that show us physical circuits are never truly ideal or instantaneous.
The physics always gets in the way.
And finally, we discussed arithmetic circuits, the real engines of computation, the number crunchers that power everything from your phone's calculations to supercomputer simulations.
Absolutely. And what's really clear, I think, is how deeply interconnected all these concepts are. You can't optimize one area in isolation. Every single decision a designer makes, choosing an FSM encoding scheme, picking an adder architecture, routing signals across clock domains, involve those constant trade-offs between speed, area, power, and crucially, how easy the system is to verify and debug.
It really hits home that designing these systems isn't just about knowing the facts from a textbook.
Not at all. It's really an art, or maybe a science, of making strategic architectural choices based on often conflicting requirements. You're always striving for that optimal balance for a given application.
And it really underscores that effective digital design is this iterative process, right? Understand the problem, make informed choices based on these trade-offs, rigorously verify those choices.
Rigorously verify, yes.
And then constantly optimize. It feels like there's been a shift, too, moving beyond just hoping you found all the bugs with simulation.
Definitely.
To actually proving correctness for critical aspects using powerful analytical tools like formal verification and static timing analysis. That seems like a massive leap in confidence for designers.
It truly is. It allows for much more complex systems to be built reliably, but the challenges don't disappear entirely. So here's something to think about. Given the inherent probabilistic nature of things like metastability and the non-ideal behavior of physical circuits that we can manage but never fully eliminate, how might future digital systems evolve? Could they perhaps become even more adaptive or even self-correcting? Could they dynamically manage some of these complexities in real time, maybe adjusting timing or logic on the fly, moving beyond just the static design time optimizations we rely on today?
Systems that adapt to their own imperfections in real time. That's a fascinating thought to ponder as you look at the digital devices all around you. Thank you so much for joining us on this deep dive. Keep exploring the hidden intricacies of the digital world.